I'm assuming you're here because you know what a cyclic triangle is, but that you like to know why any triangle you can come up with must be cyclic, and how this construction helps us prove that. We're going to do that by analysing this construction so that we understand what's going on, so that when we come back to it later, you'll understand why it proves that all triangles must be cyclic. So let's take a closer look at this construction. The first thing I want you to notice is that we have a horizontal straight line, and we've highlighted 3 points on the line, one at each edge and one in between them. And then positioned between each end point and the internal point is a vertical line. I'm going to give each point its own label, the numbers 1 to 3. And one more thing I like to point out is the left hand side of this construction does exactly the same thing as the right hand side of this construction. And so by examining one side, we'll understand the other side. So let's just explain what's going on the left side of this construction. Some of you probably already recognize what this is. We have two intersecting curves that are of the same size. The origin of the left curve is at the left end of the line, and the origin of the right curve is at the right end of the line. And we have a straight line passing through the points where the curves intersect. And in case you didn't know, this is how we construct a perpendicular bisector. The line that passes through the points where the circles intersect is perpendicular to the horizontal line, and it also bisects the horizontal line. The lengths of each side of the line are identical. Let's bring back the right hand side of the construction, and exactly the same thing happens here. The length of the line between points 2 and 3 may be different than the length between points 1 and 2, but the curves originating at points 2 and 3 are the same size and intersect. So the line passing through the points of intersect must be a perpendicular bisector of the line between points 2 and 3. Now because points 1 and 2 and points 2 and 3 are just points on the same line, the blue lines between these 2 points must both be perpendicular to the original line. And that has to mean that the blue lines are parallel, and one important property of parallel lines is that no matter how long they are, they will never intersect. These lines will never meet. This is the most important factor in our proof, and we'll come back to this later. So let's begin with a triangle. Any type of triangle will do. A triangle is a shape created using 3 points in space. Each of those points is called a vertex. Let's highlight them. I'm going to give each vertex a numbered label, 1, 2, and 3. And using the method we saw before, I'm going to create perpendicular bisectors between points 1 and 2, and then between points 2 and 3. If we place the point of a compass at vertex 1 and we draw a curve, and then without adjusting the compass, we put the point of the compass at vertex 2 and draw another curve. The two curves intersect, and if we draw a line that passes through the intersect points of the curves, we know that this line must be a perpendicular bisector of the base because points 1 and 2 are the ends of the triangle's base. Now one thing that I didn't mention before is that if you take any point on this line, let's pick a point, the distance between point 1 and this new point must be the same as the distance between point 2 and the new point. And we can prove that by joining point 1 and point 2 to that line. Now you should be able to see that this results in 2 right angle triangles, because remember, the purple line is perpendicular to the base of the original triangle, so it must be perpendicular to both bases of the new triangles. But the purple line is also a bisector of the base, which means that these 2 right angle triangles must have the same base, and they must both have the same height because the point on the line is their height. So we have 2 right angle triangles with the same base and height, which means they are identical triangles, and so the hypotenuse of both triangles must be the same length. In other words, the distances between vertex 1 and this point and vertex 2 and this point must be the same. And this must be true for any point on this perpendicular bisector because the bases of the resulting triangles will always be the same, and the point will be the height of both triangles, resulting in 2 identical right angle triangles with the same length hypotenuse, meaning the distance between vertex 1 and a bisector point and vertex 2 to the bisector point must be the same. So any point on the line will always be the same distance away from vertex 1 and from vertex 2. Now let's finish up by drawing a perpendicular bisector between vertex 2 and vertex 3 of the triangle. We'll draw a curve whose origin is at vertex 3, and then draw a curve of the exact same size whose origin is at vertex 2. We can see that both curves intersect, And then finally, we'll draw a line that passes through both points where these two new curves intersect. This line must be a perpendicular bisector of the line that joins points 2 and 3. And that's the end of our drawing. And now we can show why this particular triangle must be cyclic. And we can get rid of all the curves to make things a bit clearer. And notice that these perpendicular bisectors intersect at this point. Let's highlight the point. Now I'm just going to do some relabeling to help us understand what's going on here. I'm going to label the intersect point with the letter P. And I'm going to rewrite the vertex labels 1, 2 and 3 with A, B and C. Now we saw earlier that if you pick any point on the perpendicular bisector of a line, the distance between one end of the line and that point must be the same as the distance between the other end of the line and that point. That must mean that the distance AP must be equal to the distance BP. But the same must be true with regards to the perpendicular bisector of the right edge. The distance CP must be the same as the distance BP. Now, if we look at the equation that we've just derived, we can see that AP equals BP, but CP also equals BP. So we could rewrite this as AP equals BP equals CP. And what that means is that the distance from each vertex to the intersection point is exactly the same. And now all you need to do is make the intersect point of the perpendicular bisectors the center of a circle, and make the distance to any of the 3 points the radius of the circle. And because the distance to each vertex is exactly the same, when you draw the circle, each vertex will sit on the edge of that circle. And just to demonstrate this visually, here is a circle where each vertex sits on the edge of that circle. And now the last thing we have to do is to show why this applies to any triangle that you could possibly draw. Why all triangles must be cyclic. Hopefully you've understood that if the perpendicular bisectors of two sides of a triangle intersect, the distance between the intersect and all 3 vertices of the triangle must be the same. And so the intersect is the circle center, and the distance to all the vertices are the circle's radius. So they must sit on the edge of a circle. What I'm saying is that the perpendicular bisectors of 2 edges of all triangles must intersect. In other words, there's no such thing as a triangle where the perpendicular bisectors of 2 edges do not intersect. Remember that a triangle is made out of 3 points in space, and the perpendicular bisectors are between 2 pairs of points. In this case, the 2 points on this edge and the 2 points on this edge. Now, is there a scenario where the 2 perpendicular bisectors between these 3 points do not intersect? Well, here's where we go back to our original construction. The answer is yes. Here we have 3 points in space, and between 2 pairs of points, we have perpendicular bisectors. And we know that because these 3 points are on a straight line, these 2 perpendicular bisectors will never intersect because they are parallel to each other. And as you can see, these 3 points in space do not make a triangle. They just make a straight line. The only way you could make these 2 perpendicular bisectors intersect is if you created an angle between these 2 lines. So let's see what happens when we do that. Hopefully you can see that eventually the perpendicular bisectors will intersect at some distant point, but that now all 3 points are not sitting on the straight line, which means I can now join points 1 and 3, and that forms a triangle. So the only way we were able to get these perpendicular bisectors to intersect is if we position the points such that we could create a triangle. This means that if the perpendicular bisectors do not intersect, no triangle exists, but that if we create any triangle, the perpendicular bisectors must intersect, which creates a point that's the same distance from each vertex. That point is the circle center, the distance to each vertex is the circle radius, and so these 3 points will lie on the edge of the circle. And that's how we know that all triangles must be cyclic. Well, that's it for now. Thanks for watching.